So in this problem, we're given a function which is the cost of operating a truck, cost per hour, based on a given speed that the truck is traveling. And the question is, at what speed is the total cost per hour a minimum? So since we're being asked to find a minimum, we need to find the derivative of our function. So c prime of s should equal 0.0002 s minus 0.01. And we know that when the derivative equals 0, our function potentially has a minimum or maximum, but most likely in this case, since that's what the question's asking for, it will be a minimum. So we find that this should occur when s equals 50, and just to verify that we have a minimum, I'll do some sign analysis. If I substitute in 1 to the derivative, I get a negative number. If I substitute in 60, I get a positive number. So I verified by sign analysis that at 50, the derivative changes from negative to positive. So this means that whatever our speed units are, the minimum occurs when the speed is 50 units. Right? Whatever those speed units are, we can't tell from this problem. The second question is, what is the hourly cost to operate the truck? And so we need to figure out what c of 50 is. And when we substitute 50 into the original function, we will get 111.75. I suppose we can assume this is dollars per hour, but we're not really told explicitly. So we'll just say it's units per hour as some rate, and this is what we know. One thing that you may be thinking is that we could have found this algebraically by finding the minimum of the parabola, and although mathematically that's correct, the intention of the problem is to test your calculus, to show that you understand calculus, and so algebraic solutions will not be accepted, although they'll be mathematically correct. So we're not testing your ability to use your algebra. Let's consider a second example. Here, someone wants to add 1,000 square feet of area to their greenhouse. So just immediately we know that length times width, where'd it go? We know that length times width has to equal 1,000. We also are told that they want the border on 3 sides to be cedar siding at a cost of $10 per foot. So based on the diagram, the cost will be twice the length plus 1 of the width times 10, and that's dollars per feet, plus this final side of the building, which will be brick, so it's the other width, so that'll be 25 times W. Gives us the cost of this entire thing. And so we do have 2 equations. What we ultimately want to do is find the dimensions to minimize the cost. So if we could get this cost function to be in terms of just L or just W, we could get this done. I'm going to convert this to be in terms of just L, or just W. So I know that L equals 1,000 divided by W, which means that my cost will equal 10 times 2,000 over W plus W plus 25W. And cleaning this up just a bit, I know that my cost function will be equal to 20,000 W to the negative 1 plus 35 W. And since I want to find a minimum of this, I'll need to take the derivative of my cost function. So in this case, it'll be negative 20,000 W to the negative 2 plus 35. And I want to know, when does this equal 0? So the whole thing, they'll have to set it equal to 0, and I'll begin solving this for W. And so whatever 20,000 divided by 35 is what W squared is. So W, when I take the square root of both sides, is about 23.9047, and this will have to be in feet. And the reason I'm going to more decimal places is because I need, is because I have to use this to come up with L. So this will increase my accuracy of L by taking more decimal places than needed. I'm being more accurate. And L will have to be 1,000 divided by 23.9047. And so L to 3 decimal places is 41.833 feet. So that's what the dimensions need to be to minimize the cost. And there's the first 2 examples of economic optimization.